Okay, this is 4.1 part 2, and I'm just going to do a quick little recap here of 4.1 part 1 here. So it says, in what way does the photoelectric effect support the particle theory of light? So yesterday we talked about how light behaves both as wave and particle, okay? And so the photoelectric effect was when we have light, various frequencies shine on a metal, and some frequencies could physically emit electrons. And basically that light has to hit that photon has to hit that electron straight on to knock it off the metal, okay? So basically, for an electron to be ejected from the metal, it's got to be struck by a single photon that has the minimum energy to knock that electron loose, but it's like, it's got to hit it straight on. Okay, so this part 2, we are going to look at electrons and why they don't crash into the nucleus. And this does involve some Bohr's idea and looking at light emissions. Okay, so if you have a gas, okay, and you put it in a low pressure system with a current, you can excite those gas molecules and they will give off light, okay? You can do it with hydrogen, helium. I actually have like gas light tubes, and we do this in our astronomy class, okay? And when it's not excited, okay, it's in its ground state and nothing really is going to happen, okay? But if you add a little bit of energy to it, okay, then it's going to be an excited state, which just means that electrons, okay, have a higher energy than the ground state. And there are many, many different levels here, okay, different excited states, and you're going to learn about that in this chapter. But basically, you know, electrons, they are set in a certain energy level, and when they are moved from that energy level, then they become excited. So just, I know I'm kind of getting ahead of myself here. So ground state just means the lowest energy state of an atom. Excited state means, hey, it's got some energy and it's excited. And that's because, you know, you've added energy to it, or something added energy to it. So here's my rings, okay? And I guess I'm going to draw some things in. So if this is where my electron is chilling, okay? And all of a sudden, some energy hits it straight on, okay? And now my electron has moved from this ring to this ring. Ooh, now we are in an excited state. But that electron is going to realize, wait a minute, this is not where I belong. I'm supposed to be in this energy level. So then it's going to fall back, okay? It will eventually fall back to its original energy level. And when it does, it will emit light. And then we perceive that light. We see that light. So that's what it means by that. So if you observed energy through a prism, that light is separated out into specific colors of the visible spectrum. That's called an emission line. But the emission line was always the same for an element, which means that, like hydrogen, when you look at hydrogen, a hot gas, it's always got the same bands. When you looked at helium and you excited it, it always had the same bands, and so on and so forth. So like every element on the periodic table, it basically has a fingerprint, an emission line spectrum, a unique emission line spectrum fingerprint. Okay, so this is what they're talking about. Here's my hot gas. And if we just have this narrow band of light and we hit it through a prism, okay, we are going to see specific bands. So this is hydrogen. Okay, so when you excite hydrogen, it's got this pinkish glow, and we pass it through a prism, and these are the frequencies that we see. So this is hydrogen's emission line spectrum. So here's hydrogen, okay? Here's heliums. Here's neons, sodiums, mercuries. Now these are cartoon diagrams, okay? There might be a few more bands, but each element has a unique emission line spectrum, and this is how astronomers figure out what distant objects are made up of. Okay, they look at the light, put it through spectrum, okay, they analyze it. Okay, so if you were looking at an object up in space, or maybe a mixture of a gas tube in lab, and you saw this, what could you say, what gases make up that emission line spectrum? And you'd say, okay, well, see the double purple, so hydrogen, and looks like neon, double red. So this is a mixture of hydrogen and neon. So it's just talking about how, okay, gas, when it's at its lowest state, it's not going to give off any light, but when you add energy, I thought I had my arrow, fix that. It's going to be an excited state, and in that excited state, we see light. So under what circumstances can an atom emit a photon? Well, when light shines on it, right? When some photon hits it, and that electron goes to a different level, and then it falls back. Okay, so emit a photon, hey, it's going to give out that energy that it received. I should have done the same color to show that it was the same energy. Okay, so Niels Bohr comes along and he's like, okay, so we got these electrons, okay? And I kind of, how did we know that those electrons were in the rings? Well, we didn't at the time. I was just trying to show you how an atom can be in the ground state to an electric state, okay? So Niels Bohr links energy states to photon emissions. And what he did is he took electrons and he circled the nucleus in orbits. So those rings that I drew with my electron, those are actually called orbits. And you notice that they were definite, they were fixed, and the higher energy is farther away from the nucleus. And these electrons, they orbit that nucleus in different energy levels. An electron, if I go back to the side, can't chill out here. It's got to be on the ring. Can't be mid-ring at all. So they can't orbit midair. They can't orbit in between. They're either in this energy level, or this energy level, or this energy level. So you can kind of think of it as like rungs of a ladder. Set energy levels. The electron's either here or here. It's not mid-step. So electrons are in orbit. It's not gaining or losing energy. Energy has to be added to that electron to go from a lower energy to a higher energy. We call that absorption, and it becomes excited. Okay, so we go from ground to excited state. And when that electron falls back, they emit a photon, and we call that emission. And the difference, okay, between the initial high energy state and the lower high energy state can be measured by Planck's constant. So we can quantize that amount of energy, that photon. So hopefully that's kind of all coming together here. All right, so how can energy levels of an atom be determined? By measuring the light from an atom? Well, excite it, figure out the amount of energy being given off, okay, and then measure it. So when it loses that energy, it's going to fall back down to its original ground state, and you can analyze that frequency and plug it into Planck's constant. And that does it for part 2. Okay, and then we would finish reading the book, and then you would do the book worksheet. Now, actually, I should probably pull up the book worksheet. You're going to have to give me a second here. This is going to get really weird because I should have pulled it up earlier, and then I have to slide it into this little narrow window here. I want to see that. Okay, so this is what the assignment looks like. Okay, it's got page numbers in your book. You want to use your book. Okay, kind of goes in order. I want to talk about this back page. Okay, number 11. How many different photons of radiation are emitted from an excited helium atoms to form the spectrum below? These are bands. Okay, the white stuff are the bands. Count the bands. Okay, and it's kind of like the emission spectrum, but it's black and white. I'm sorry, it's not in color. Okay, this part down here. Characterize each of the following energy level changes, either absorption or emission. So absorption, okay, is when you go from a low energy state to a higher energy state. And emissions, when you're going from a high energy state to a low energy state. So this E is supposed to like stand for energy, and the two, think of it like as rungs. You're in the second circle from the nucleus, and the 1 in the first circle. So to go from 2 to 1, oh, we are falling back down. So this would be emission. To go from 1 to 2, oh, we are absorbing energy. Okay, and then there's questions down here. It says, which of the energy changes above, A, B, or C, these right here, emits or absorbs the highest energy? So you want to look at emits or absorbs the highest energy, the biggest step, like the biggest difference. And then this would be the smallest difference. And I can already tell that there's going to be a tie for 15. Yay, I should have changed that. Maybe I'll change it for the other class. And yeah. But anyways, that is the worksheet, okay? But definitely use your book.